name is Catherine. I am an OpenSciEd teacher, facilitator, and writer. And in this video, we're going to talk about lesson 7 of the P.1 electricity unit. I love this lesson because it gives students a chance to start to think about how do we actually use the knowledge that we've been gaining to try to explain this phenomenon that we've been seeking to explain. So let's take a look at how we get here in lesson 7. If you recall last lesson, lesson 6, we played with this simulation and figured out that electric and magnetic fields are going to change and transfer energy in and out of them. And these electric fields are going to actually push on the electrons. And this is what we refer to when we say electrical energy. And that these electrons, as they're being pushed by these changing electric fields, are going to continuously move or slosh back and forth within the wire. And this is what we refer to as heat lost to the surroundings, as those moving electrons are going to heat up those atoms of the wire material. And so now in this lesson, we're asking ourselves, okay, we know all of this information about electricity and electricity transfer and electricity generation. Can we actually answer some of our questions that we had back in lesson 1 that are over there on our driving question board? So let's take a look at how this happens in lesson 7. This is a 2-day problematizing routine lesson. And when we say problematizing in OpenSciEd, what we mean is the opportunity to have students take stock of what we think we know, try to use what we think we know to explain the thing we've been trying to explain, and then walking away with some questions that remain that we still need to explore. And this lesson, while it does not have a hands-on investigation, it does have a hands-on teacher demo that does require some setup and preparation on your part. And there is an additional video linked in the teacher edition for how to set up this teacher demonstration. And then lastly, students will need access to devices on day 2 as they explore some data with a tool called CodeApp. So throughout these 2 days here in lesson 7, students are engaging in 2 key sense-making loops. The first one is going to occur on day 1, where students have the opportunity to try to model individually and as a class and with our electric city model from lesson 2, what actually happens in times of insufficient supply and high demand. And through these processes, we realize that humans have to be involved and humans have to make some decisions on where energy should go when there isn't enough supply to go around. And this means some places are going to receive energy while others are not. And then we take that information on day 2 and we wonder, well, how did people in Texas make decisions? And we look at some data on the counties across Texas and the percent of power outages that they had. And we try to identify a variable that gives us a strong correlation coefficient to say that this is a causal relationship. And we realize that out of all of the variables in all of this data that we test, there isn't one that actually helps us determine this is the one cause of what happened in Texas. So we walk away in lesson 7 figuring out that the county level data that we looked at with this CodeApp data exploration tool shows that there's some disparities between counties, but we can't really explain that well with our electric city model, and we don't really understand well the causes of those disparities at a county level. We realize that power companies in Texas had to make some choices about who lost power and who did not, but we're, again, unsure how they made those choices. And that through all of this, there's no one factor that explains something. So we need to think about our data perhaps on a different grain size if looking at it at a county level did not actually help us in identifying the factors used to decide where that energy went and where it did not. So let's take a look at these 2 key sense-making loops a little bit further. The first one, again, is happening in day 1 over the course of parts 2 and 3, where students are modeling on their own and then together as a class what insufficient supply would look like. And students do this, again, as I mentioned, as a group and then as a class. And throughout this, what's really key is identifying what we as a group think are the systems or subsystems that we should include in our component boxes. How are we going to quantify energy transfer? We've thought about this before. We maybe as a class came up with one convention to use, maybe we didn't, but now let's be clear on the convention that we think makes the most sense, and how we're going to use that energy convention to not just quantify energy, but to show how it's distributed and how there might be a difference or an inequitability between that energy distribution in terms of supply and demand. So I have an example here of what this could look like for you and your students. I'm using color circles to quantify energy. I am using a solid circle to show this is the actual supply that is there and available versus the number of circles showing the amount that should be there or the amount that would be demanded. So in this situation, our source isn't providing enough energy for everyone, and our two houses over here are without power while our hospital is at full power. And through this conversation and trying to model this out as a class, we realized we're still unsure how this actually happens. This is something that occurred in theory, but do some of these houses, can they get a half a circle? What might that look like? So we decided to actually test this on our community grid, that electric city that we have set up, or we pull back out from lesson 2. So in our electric city model, we have the chance to actually measure demand using a device called an ammeter. And the higher value on it is going to mean that there's more demand being met. And we use a hand crank generator as our power source here, and we have a couple of areas identified. We can reduce the amount of energy that we put in or increase it to meet that demand based upon how we're spinning our hand crank generator. And if we're not spinning it as fast as we can because we're trying to model low supply, we need to decide where are we going to send the energy, because when it's not spinning fast enough, I don't have any lights on. I need some lights somewhere because this thing is spinning. So we have to negotiate together where we're going to send that energy. And we decide as a class, let's send it to what we think is most essential, like a hospital. So then we start to wonder, well, is this what happened in Texas? And then that brings us to day 2 with our CodeApp data analysis tool. We introduce this as a whole class and model what using the tool looks like to graph percent of county with power outages on the y-axis versus number of hospitals on the x, and then how to use the tool to calculate your R-squared correlation coefficient value using a best fit line. And then students work in small groups to choose from a variety of potential variables that they think might have been used to guide the decision-making of these power companies. And we realized that there isn't any variable that actually yields an R-squared that tells us this is the thing that caused power outages. And so in part 9, we discuss as a whole group, what is the limitations of our data? And so we have questions like what limitations might be introduced by the fact that our data is grouped by county, as well as what patterns do you think we would see if we could zoom into these counties? And this is an image of what one of those zoom into a counties might look like. And the goal here in this conversation is to pre-assess how well students understand the distinction between data at various grain size. A larger grain size like a county versus a smaller grain size as like a neighborhood. As lesson 8 is going to provide a better understanding of this, but this discussion here in part 9 of day 2 helps you see where students are on their own first. So from here, we figured out that we are limited by the data grain size that we have. So we wonder what this data might look like at a smaller scale and see if we can explore that for next time. As we wrap up here, let's talk about some material management tips and tricks to be successful. And really, you want to focus on part 4, which is testing our supply and demand model on Electric City. Again, you'll watch the setup video for this and be sure to test your city beforehand. You want to make sure that one of your areas has been designated as a hospital ahead of time, especially if your students did not choose to add a hospital as an important community building in lesson number 2 when we did this to begin with. You'll want to practice how you crank that generator harder to get more current. It's going to be more difficult, physically difficult, if there are more light bulbs connected to your system. So know what your limitation there is. And if you have an ammeter, make sure you have it set up so that you can read it, or a good quality multimeter will work here just fine. For our glossary, we do add the words hypothesis, correlation, and our R-squared value that come from our discussion of our CODAP data. And then in terms of material or resource management, there aren't any posters for this lesson that we need to reference or save, but we do need to pull out our Electric City or set up a similar demo one. We will also add to our progress tracker. Thank you for joining me, and I hope to see you in the next video as we start to explore what might this data look like at a smaller scale.